So welcome to the seventh and the last video for the E114 power engineering module, and now we will talk about the induction machine. So the induction machine is first of all primarily an AC machine, and note that it won't act as a generator in usual mode. Usually when you say induction machine, you would mean an induction motor. So, like in most induction machines, the stator sets up a rotating magnetic field. We have seen how it does that. If you have a three-phase winding in the stator, it can set up a magnetic field that rotates in one direction. The speed of that rotation we saw is 120 F over P, the synchronous speed, right? Now, the rotor in an induction machine is not like that. It's just a group of windings that is mechanically attached to the shaft and it is shorted at the ends. So it's just a group of coils lying in a magnetic field that is varying with time. And since it's varying with time, the flux changes and hence EMF is produced, the currents flow in the rotor. And these currents experience a force. So that is what produces a torque in your induction motor. Now, since there are currents flowing in coils in the rotor, these also produce some flux. And now we can draw a phasor diagram with respect to the rotor. So assume that the flux that was being produced by the stator was in this direction. So since E is minus d phi by dt, the derivative would take 90 degrees phase shift in forward direction. The minus would bring it back 180 degrees. So this is the direction of the induced EMF in your rotor, right? This is the phasor for that. Now, suppose that the rotor is mainly resistive, but since it is made up of coils, it will also have some inductive impedance. So that means that the current is lagging by some angle. We will call it delta for the time being. The current in the rotor is lagging the EMF by some angle delta. And since the current is exactly in phase with the flux of the rotor, because if you can see it, the current produces the flux in the same phase. So hence the flux also points along this direction, right? What this means is that the angle between the stator flux and the rotor flux is 90 degrees plus delta, and we have seen that if there are two fluxes which are having the same frequency, and these must be having the same frequency, and the reason is that we have been drawing a phasor diagram, and the basic crux of a phasor diagram was that everything has the same frequency, right? So since these have the same frequency and there is an angle of 90 degrees plus delta, that sine of this angle becomes cos delta. So the torque is proportional to cos delta, right? So as you change this angle, a qualitative way to interpret the torque would be that it changes as the cos. Now actually it would be more complicated because this flux's magnitude would also be changing. So there are a lot of things going on. We will derive the formula for torque. But notice that we cannot talk about the phases in the rotor right now, but it will also make a wave. Okay, it's not just that it is simply having some sinusoidal flux. No, it is also producing an MMF wave. There are two MMF waves, the stator and the rotor, and they are at some 90 degrees plus delta angle. So that is why they are producing some torque. Now notice that I've been drawing these at some angle, right? But if you thought of the rotor as being completely uh, resistive in nature, then you would have seen that this phase would come along here, and had it been completely inductive in nature, that flux would have come here according to what we have been talking. And the flux coming here makes sense. Why? Because that is what Lenz's law says, right? If you have some flux and that is changing with time, what your phasor would like to do is try to negate it. It would try to pull it down. So yes, the directions do make sense. Now, the basic condition was agreed, right? The rotor has, according to the rotor phasor diagram, the two fluxes are having the same frequency. But what is that frequency? So that will be related by this small simple variable called the slip. So the above diagram was with respect to the rotor, right? Now the stator we know generates the MMF wave at some synchronous speed omega s, but we do not know the rotor's point of view because now the rotor is rotating at some speed. And since the rotor is rotating, it sees the stator MMF wave move at some smaller speed. And see, the speed at which the rotor sees the MMF wave move is the frequency of the whole rotor phasor diagram, right? The rotor's phasor diagram is at the same frequency as the speed at which it sees the stator MMF move. And the reason is that that is what created all the phasors in the first place. If you remember, all these phasors were produced by this flux, and this flux was being made by the stator. So that's why the speed of everything, right? The frequency of everything going on in the rotor is this relative speed by which the rotor sees the stator MMF move. So now the rotor sees the MMF wave rotate at some slip frequency. It is less than 1, that S is less than 1, this factor, and that S omega S, which is less than omega S, is that frequency at which all the currents and the EMFs in the rotor move. Now, according to the principle of, relative motion, we can see that the rotor itself must hence be rotating at omega S minus S omega S, right? And this variable S is called the slip. Know that if S is 0, what will happen is there is no relative motion between the stator MMF wave and the rotor, because see, the rotor sees the MMF wave rotate at this slip frequency. If this was 0, then it doesn't see the MMF wave rotate, and if it's not seeing the MMF wave rotate, it is not a time varying magnetic field, it is constant in time, and that means that the EMF produces 0, the current produces 0, there is no torque, right? So some people try to argue that this is the case because the angle between the two fluxes becomes 180 degrees or something. So that is not the case. The EMF produced itself becomes 0. Now we talked about the phases in the rotor, right? So how do we try to find the phases in the rotor? Because we said that it produces a MMF wave, but that means it should have three phases, right? So one way to argue this is that, you explicitly make the winding a three-phase winding. You actually draw the leads and then you just short the leads, right? So actually make the rotor winding as complicated as the stator winding, but then instead of supplying power, what you do is you just short them manually from outside. So this is called a wound rotor, and this would become a wound rotor induction machine. The thing is, this is more expensive because you are now making two complicated windings, and the rotor is very high maintenance in this case because you have to take it out completely if you want to do anything on it. But it provides a better starting, and we will see how it provides a better starting. Starting means that it is easier to start a wound rotor. It is more complicated to start a squirrel cage rotor. So what is a squirrel cage? What you do is you just use rods and you connect them at the end with rings, right? You just take many rods and you put them in a circular fashion and connect them at the ends with rings. So I will show you a photo later, but this is what a squirrel cage looks like. So it's called a squirrel cage rotor. It is much more rugged. The rotor usually doesn't have any damage whatever you do to it, and it is much cheaper than the wound rotor because, well, you are using very simple windings now, and its starting can be made better. So in wound rotor, you have made it explicitly three phase, but in a squirrel cage, it can have as many phases as their rods, the number of rods per pole. It can have as many phases as that. But you usually take an equivalent wound rotor when you're considering actual induction machine equivalent circuit. So this is what a squirrel cage rotor looks like. Notice that these are actually at an angle. And this angle is because what can happen is the rotor MMF and the stator MMF can get linked together. And what that will cause is that it will try to stop the rotor itself from rotating, right? If their MMFs get linked together. So what this slight angle does is it tries to push them out of phase here and here, right? So there are more than one stator teeth in front of a rotor teeth right now, so their MMFs cannot possibly get locked. Now we talk about the equivalent circuit construction. So the first step is you take a generalized transformer. What is a generalized transformer? It is a transformer which can also change the frequency of the electric current and voltage you are providing. And we are using this because, well, the frequency of the rotor and the stator are different now. So that's why. And now you draw the rest of the power mechanically. So the generalized transformer is also spitting out some power, right? So it is supplying some power to the rotor circuit, and the rest of the power was being drawn out by the shaft. So that is coming out mechanically. So there is some power that is not going into the rotor circuit, right? It's not a power invariant system. Now you compensate the turns ratio first, because now after that we will have a transformer that is having unity turns ratio. That is much more easier. And now you talk about the referred variables of the rotor. So when you refer variables, we talk about the variables that were in the rotor referred to the stator. If they were in the stator, how would they behave? Now notice that the rotor was running at S omega S. It was not running at omega S. So all the referred variables are at omega S, but when they are in the rotor, they are at S omega S. So the frequency is different. And here is the biggest step. This manipulation is what is hard to understand. So see, the current in the rotor, right? If you refer it, it is of this form. Now why have I put S here? So if you refer the voltage would be at the frequency of the stator. But the actual rotor voltage is at the frequency of the rotor, which is s omega s. And note that since E is d phi by dt, it is proportional to the frequency. And frequency is not omega s in the rotor, it is s omega s. So to compensate that s, I put an s here. Also notice that since the inductance has an impedance j omega x, so it's basically s x2 prime instead of just x2 prime, right? So when you write it like this, the current becomes like this. The x2 prime is imaginary here, there is a j inside here, but if you divide up and down by s, you can write it like this. And observe that now you have e2 prime here, it is not se2 prime, which is at the same frequency, right? E2 prime was at the same frequency as the stator. So now you have a transformer which has a unity turns ratio and which also has a unity frequency ratio. So now you can just kick it out. There is nothing involved here. Just note that now the rotor has an impedance which is given by this, right? Now this step was not power invariant because you see the power into the current into the voltage, that thing is not constant. E2 I2 prime is not constant. It is having an S factor getting removed. So that S factor is what actually does a very important thing. What it does is that it consumes all this mechanical power also into the rotor circuit. The generalized transformer was spitting out some power mechanically to the shaft, but when you do this step, all that power is also going into the rotor circuit. So we now need to distinguish in the rotor circuit the power that was being drained by the rotor originally and the power that is actually coming out mechanically to the shaft. To do that, you write this R2 prime over S as two parts, R2 prime plus R2 prime 1 over S minus 1. So that R2 prime into I2 prime whole square is actually the power that was being consumed by the resistor earlier also in the rotor, I square R. But that extra R2 prime 1 over S minus 1 is what is actually giving the power to the shaft. So now we just need to remember first of all that this circuit that we drew, that is a per phase circuit, right? So if there are three phases, you need to multiply whatever you get by 3. The power that you will get from this circuit is just 1/3. You will have to multiply that power by 3 if there are three phases. If there are more, multiplied by that, the number of phases. So now this is our final equivalent circuit, right? This is the leakage inductance, this is the leakage inductance, this is the resistance in the stator, this is the resistance of the rotor over S, and we will write this as two things, R2 prime and R2 prime 1 over S minus 1. R2 prime is the power going into the rotor and the rest is the power that will get in the shaft mechanically. This is the magnetizing branch, this is RC and this is GXM. Now the power and torque. So the net power through the air gap is 3 times if you actually calculate. Now this is per phase, so that is why I multiplied by 3. This is the Thevenin equivalent circuit. So now let me explain some terms that I've just thrown around. So first of all, what is power through air gap? So you see when some current comes in the stator and now this is the rotor referred rotor variables, the whole power going in this resistor is called the power through the air gap because that is the amount of power that the stator is managing to flow through the rotor. Now the rotor has two places where it is giving that power. It is giving it to the shaft also. It is also dissipating it in the windings. But all the power that the rotor receives through the air gap is this R2 prime over S. So if you want to calculate the power given to it, what you can do is that you can just take this part, right, and you take the Thevenin equivalent of all of this, right? So across these two terminals, you take the Thevenin equivalent. So you have a VTH, you have an RTH, you have an XTH. And then you calculate the current and hence R square R2 prime over S would become the power through the air gap. You multiply that by 3 because it was per phase. Now this looks ghastly, right? But it isn't that bad and you will see why. You can draw its graph and that graph is what you will actually need to remember because that graph is what will give you all the important points. Now see, the power to the shaft was basically R2 prime 1 over S minus 1, right? There was a 1 over S minus 1 factor. So you could talk of it as 1 minus S. The power to the shaft is this power into 1 minus S because that is all the factor that will get multiplied and the rest will remain the same. Now the torque is the power to the shaft by the angular frequency of the shaft because that is the fundamental equation, right? Power is torque into frequency. So that now tells me that if I wrote PS as 1 minus S, these 1 minus S would be getting cancelled and you will get this P air gap over omega S term. This is the main torque equation from which you can take the ghastly formula and put it here. This is called the torque speed characteristic. Why is it called the torque speed characteristic? Because it is a graph between the torque and the speed or the slip of the induction motor. So now there are two important points in the graph that I will point out when we get to the graph, that is called the maximum torque and the starting torque. So this is your top speed characteristic, right? When the rotor isn't rotating, its angular frequency is 0. When it is rotating right at the synchronous frequency, its ratio with the synchronous frequency is 1. Now at this point the slip is 0, the slip is 1. If you go over here, the slip increases. If you go over here, the slip is negative. This is what the torque speed characteristic over all regions looks like. At s equal to 1, the rotor was actually standing still, right? Because it was not rotating. So this is called the starting torque, because when you start a motor, the rotor isn't already rotating. So this is called the starting torque. This is called the maximum torque that you can achieve by that system. And the slip at which it occurs, the slip, is called the stalling slip, or the speed at which it occurs is called the stalling speed. Because if you try to get more torque out of it, the motor will simply fail. It will say, I can't do it. It will die down. Now notice once again that if slip is 0, the torque is 0, which is what we intended. So yes, we are getting some rational results out of this. Now just like the transformer, there are two tests in your uh, induction motor also. So we first get the equivalent circuit, because then it's easier to understand. The first is the blocked rotor. So you, as the name suggests, you simply block the rotor from moving. So now the slip is permanently 1. Right. This means that just like in the case of the transformer, since these are much smaller than the magnetizing branch impedance, you say that this is so large that very small current is flowing through here and we ignore it. Similarly, there is something called the no-load test. You let the rotor move at whatever speed it wants. So now since there is no load, it moves almost at the same speed as the synchronous speed, which makes the slip so small that this branch has now a very high impedance, which lets you ignore the current through here. And if you ignore the small impedances which are in series, you can get the impedance of this magnetizing branch also. So the primary impedance is getting ignored. Now we come to the most important point that we have been talking about, the starting of an induction motor. So the first and the last thing about starting is that the starting current of the stator is usually 6 to 7 times the usual starting current, right? If you plot the current, it actually looks that it is 6 to 7 times normal, and then after about 10 seconds it comes down to the normal starting value, the normal operating value of the current. But at starting, the current is usually 6 to 7 times the usual. And we need to reduce this, because this could burn the windings of the stator, not the rotor, because the rotor, if you remember, we usually use squirrel cage rotors, and those are simply rods. Okay, they don't, nothing happens to them. So now the first way is to reduce the voltage, because the current is proportional to the voltage. Reduce the voltage, reduce the current. But the torque is proportional to the voltage squared. So you are reducing the starting torque by a lot. And if the starting torque is too low, the motor won't run at all. It will simply block. It won't run. It will simply lie there. It won't start moving. So that's not an effective strategy. What you can do is that you can use star delta starting. So what is star delta starting? Well, the stator has three-phase windings, right? So it has three different windings, and hence each winding has two terminals. We have six terminals. Now this can be looked upon as a balanced load, and you know that in a three-phase circuit, the load can be connected as a star or a delta. Now, why is this beneficial? So usually the rotor or the motor is run as delta, right? It is connected as delta. Why? Because it has more voltage, it has more torque. But if you want to start it, you can use star formation of starting. So why is this better than reducing the V? Because it looks like we're just reducing the V by √3 factor, and the torque is getting one thirded, and the current is also getting 1 over √3. But that's not the case. If we actually calculate it, the current also becomes one third. It is not reducing by a factor of √3. It is actually getting one third. So it is a bit better, because even though the torque is getting lesser, the current by that comparison is getting much lesser. So your starting current is reducing by a lot. So it's a better way of starting. Now you had a wound rotor, right? We are talking about squirrel cages until now, but if you had a wound rotor, all you have to do is add an extra impedance with that rotor, because now you have the leads that come out of the wound rotor, right? Instead of shorting, you put a resistance. What it does is it also reduces the current, but at the same time it increases the torque. So this is very good, right? If you have a wound rotor, all you have to do, put some resistance in series. That's it. the starting will be very smooth. So that's why we had said that if you have a wound rotor, the starting is very nice. If you have a squirrel cage rotor, you have to do this weird things. And star delta is not that easy because flipping from star to delta instantaneously is going to take some weird mechanics. So we usually use relays for that, but star delta is a bit harder than just adding a resistance in the rotor, obviously. So this is the end of the power engineering module. Thank you.